Series fan terminals have lower system pressure requirements because the air handler only delivers air to the unit and the unit fan moves the air the rest of the way to the room. The fan runs to provide constant volume, resulting in more air changes and higher occupant comfort. Since the fan isn't cycling on and off, it provides a constant background sound level to the space. These are all advantages provided by series fan boxes. Parallel fan terminals have higher system pressure requirements because the air handler moves design air all the way to the room, just like a single duct box. In fact, the cabinet designs of most parallel fan boxes require more system pressure than single duct VAV boxes. The higher the pressure drop is downstream from a parallel box, the higher the leakage will be through the backdraft damper. Since the air volume on the diffusers may vary during cooling and suddenly increase whenever the fan switches on for heating, extra care must be taken when selecting diffusers. The modulating airflow and unit fan cycling can result in significant sound level changes. These are all disadvantages of parallel fan boxes. When selecting fan-powered units, you'll have a choice between two different types of fan motors. The standard permanent split capacitor, or PSC motor, has been around for many years, but the newer electronically commutated ECM motor is taking over the market. ECMs have a higher initial cost, but provide many benefits for the building owner. First, let's look at the old technology. PSC motors are sleeve-bearing motors. Although they're classified as high-efficiency motors, that's really only when compared to other induction-type motors like shaded pole motors. The efficiency of a PSC motor is 20 to 60% depending on the operating condition. When properly sized and applied, they typically last 10 to 12 years. They last longer and run cooler when working hard and operating at higher speeds. The common means of speed adjustment for a PSC motor is a silicon-controlled rectifier, or SCR. This is a device that takes in smooth AC sine wave power, and as you turn it down, it notches and distorts the wave to reduce the available power to the motor. This not only reduces the speed of the motor, but it also makes the motor run hotter and can also make it hum. SCRs are best used for trimming the speed of a PSC motor rather than chopping it. Oversized PSC motors running at low speeds tend to overheat and fail prematurely. Now let's look at the newer technology. ECMs use ball bearings and include a programmable controller. Programming coefficients are developed by each terminal unit manufacturer to optimize the operation of the ECM in each of their applications. Although these motors are supplied with AC power, they internally rectify this and operate on DC power. These are smart motors that can be programmed to supply constant air volume despite changes in external pressure. They are about 70% efficient over their entire operating range, with an estimated service life of 20 to 30 years. Speed adjustment is made by means of a pulse width modulated, or PWM, input signal. Most manufacturers offer the option of a manually adjusted PWM speed control or a model that can accept a 0 to 10 volt DC input signal from a digital controller. So you can see why ECMs are taking over. Building owners looking to save on operating and maintenance costs want ECMs. ECMs are already a code requirement in states of Washington and California, as well as the city of Houston. As industry works to further reduce energy usage in all types of buildings, ECM motors become an obvious choice. Now let's look at fan selection. This is a typical fan curve for a PSC motor. It provides the manufacturer's recommended operating range of CFM versus external static pressure. As external pressure increases, the CFM delivery decreases. The top curve shows the maximum air delivery, and other curves describe the effects of 1-row and 2-row water coils. The bottom curve describes the minimum recommended operating point. Although most designers select fan-powered units for a 1/4 inch of discharge pressure, actual operating conditions can be much lower. Care must be taken to ensure that any boxes selected near the minimum curve won't end up operating below the curve under actual job site conditions. For longer life and highest efficiency, PSC motors should be selected near the upper curves if at all possible. ECM curves look very different from PSC curves. As you can see from this example, ECM curves tend to be very flat over the recommended operating range. This is because they're programmed to automatically compensate for changes in external pressure. Of course, at some point as the pressure rises, the ECM runs out of horsepower and the curves nose over. You might also notice that the operating range of the ECM is wider than the PSC motor. This is because the ball bearings and PWM speed control allow the ECM to run at slower speeds with no adverse effect on service life. Now let's go ahead and make a selection on a parallel fan-powered terminal. So if we select on our fan-powered unit, we go to Digital Control, and we select one of our parallel units. Here's one that ends in a P, that's parallel. We input our design primary airflow. Let's say that's going to be 1000 CFM. We put in our design fan airflow, and we know that's usually going to be about 50% of our cooling design, so we put in 500 CFM for our fan. Then we put in our minimum flow, which is usually 20 to 25%. We could say 200 CFM. We're probably going to want to leave our inlet static pressure at 1 inch for a parallel box, because remember, the air handler, when it's feeding a parallel box, has to move the air all the way to the room. So we're back from the lower pressure we could have with a series fan box to a higher pressure that we would need for a parallel fan box. We'll go ahead and leave our downstream static pressure at 0.25 inches. And once again, we have our choice of either a standard or an ECM motor. Let's go ahead and pick an ECM motor this time. We've also got our option for whether we want a filter on the unit, and we've got those same lining options that we've seen all along. Now if we go ahead and calculate, you'll see that the selection that came up is a unit size 4 with a 10-inch inlet. You'll see the minimum pressure is quite a bit higher than a series fan powered box. Here for a parallel, it's 0.22 inches. Once again, we have our radiated sound power. We have our room sound pressure levels. We have our radiated NC level of 32. We have our discharge NC level of 20. Now if we wanted to look and see what difference it makes when we add a coil to this unit, we can go over here and select a water coil and hit our edit screen. Once again, we have our choice of analysis methods. I'm going to go with the straight calculation. We default to an entering water temperature of 180 degrees. We have an entering air temperature of 55 degrees. Our minimum primary flow is 200 CFM. Our coil is going to be positioned on the induction port of this unit. That's a little different. We do something a little different for parallel boxes. The preferred position for a hot water reheat coil on a parallel box is on the induction port. On a series box, it always goes on the discharge of the unit. It's a little bit more efficient to pull the plenum air through the coil and then over the blower rather than push our cooling through that coil on the discharge of the unit. But one thing that we kind of the downside to doing it this way is we're somewhat limited on the amount of heat we can have in the coil, because we think that if our leaving air temperature on our coil exceeds 130 degrees, we might overheat our fan motor. So that's why our selection program looks at the leaving air temperature to make sure it doesn't go over 130 degrees. We can input our maximum gallons per minute. Let's say we put in 3 gallons per minute and we have a 1-row coil. Then we can go ahead and hit accept and calculate. And once again, we're back to our unit size 4 with a 10-inch inlet. We can look at our heat results. We have a 1-row coil with 20 MBH. That's at 3 GPM. We got a box leaving air temperature of 89, which is just 1 degree below the maximum we'd ever want to see, which is 90 degrees. We've got our entering air temperature going into our coil at 65. That's the mixture of return air from the plenum plus the cold air from the primary. We have our leaving water temperature at 166.7 degrees. We have our water pressure drop at 1.9 feet, and the air pressure drop through our coil is 0.03 inches. So that's how we would do a parallel selection.